thank you for attending here. I'm grateful and honored to be presenting here. I would like to thank Sergio for inviting me. I'll talk about this usually not known field, quantum-inspired super-resolution microscopy, taking the hook from Carmen's presentation. She talked about using a quantum sensor to measure a classical system. This is kind of related. This is not like an official name. It's just a name that I like. A few people have used. Sometimes they just say quantum super resolution. I think this inspired part explains a lot of things. And I worked this during my PhD. I no longer work with that, but I want to keep working with that. It's a very cool field. It's very recent, and I would do this like a tutorial to everyone so we can get what this is about, where is it, and where it's going. So just as to start, this all started with this paper, 2016 on PRX, the quantum theory of super resolution for two incoherent optical point sources from Kate Sang. And he basically took the classical microscopy problem of resolution. He applied quantum metrology to it. And he found very interesting stuff, basically new ways to achieve super resolution. And this gave rise to this field. And this field is called quantum-inspired because we use the quantum tools, quantum theoretical tools, to study a completely classical problem, which is the classical microscopy imaging for incoherent light. Of course, there are extensions to quantum light and everything, but the bulk of this is classical. And the paper drew a lot of attention initially, and as you can see by I don't know how to make the thing here. Yeah, you can see get a lot of attention for the citations. It kind of stabilized in the last few years. I think it died down a little bit. People maybe lost the enthusiasm or something. But it's still very promising, and I think it has a lot of challenges to overcome. But there's also a lot of low-hanging fruit. So if everyone wants to dip their toes on this, I think it's very nice because you can have a lot of results very easily, and there's a lot of things to work on this. Just to give a brief feedback on how I ended up working, sorry, a brief overview of how I ended up working with this, just to explain a little bit also the whole point of the presentation. I did my undergrad and master's here in Fisk, and I was a theoretical physicist. And then during my PhD, I took the bold decision, or deranged decision, to become an experimentalist. And it was hard in the beginning, but I adapted, and I think he wired my brain on a lot of stuff. And my supervisor used to say, I know I'm in a theoretical physics institute. That might sound offensive, but this is just personal. He told me that now I would become a real physicist. But it was a very cool experience. Then the pandemic happened. It forced me to become a theoretician again. And then I was oscillating both worlds. And then for the postdoc, I'm just doing coding now for some biology lab. So I keep changing fields, but everything around microscopy. But the point is that this field started very theoretical. They started a few experimental implementations, but there's still, I think it's a bit stuck, not being too practical enough. But I'll talk about this later. Just a brief overview. I'll give a few reviews of optical microscopy and quantum metrology. Just to make everything, have a common ground for everyone, so everyone can understand what I'm talking about. Might be too trivial for a few, but it's good to review the basics. Then I'll talk about this discovery by Tsang, about the started field, then all the progress on theory and experiment, and the future directions that the field can take or should take. So just a brief review of optical microscopy. We have the classical setup. We have our sample that are illuminated, or you can think of it just as source of light. We look at the far field, and we have the aperture, the microscope aperture. We focus the light some image plane so we can see the light. And you can see what's happening in the sample. So it's good to lay down, because this is important, the hypothesis for the setup. So the samples are uniformly illuminated. There's no engineering on or fancy engineering on the illumination. In theory, you just say it's a constant function. They're emitting incoherent light. You can think of fluorophores or thermal emitters, something like this. And this light is collected in far field, so there's no cheating. You cannot go to near field. I mean, it could, but this is focused on far field, simpler. And we are only working with linear optics, so no fancy nonlinear specific effects. And we do direct intensity detection. I put here, like in old days of microscopy, just your eye, and then you write stuff down. But it could be a camera, photodetector, just the typical stuff. Then you have the aperture problem, the resolution problem, because the aperture is not infinite in diameter, so it's basically a band limiting factor. We lose high frequency information, basically blur the images. So we lose resolution. There's a limit to resolution, so we want to know what's the best resolution we can have for a given microscope. And this is dictated by the wave nature of light because of diffraction. Want to know what's the effective resolution and what's the best achievable resolution we can get. But to know which resolution we can get, we need to define what is resolution. And you have the classical Rayleigh criterion in 1879, very old, everybody uses it. It says that the smallest resolvable separation is when you have two sources, they are convolved by the aperture, you have the point spread function, they become blurry. And if they are separated enough, you can tell them apart. It's very easy. If they are just separated, so we say that when the maximum of one source coincides with the minimum of the other, then is the resolution limit. And anything less than that, we cannot tell apart if this is one source or two or three or whatever. And this is dictated by the angular aperture, called numerical aperture. It's related to the separation of the sources and the aperture diameter and the wavelength. And this limit has been, there's also other stuff limiting resolution, like aberrations and everything, but the fundamental limit is the diffraction limit. And for optical microscopy, this is more or less 200 nanometers. We can have numerical apertures up to 1.5 if you consider oil immersed ones. But and for visible wavelength, you can get more or less around 200 nanometer. And this is very little. Like this limit has been achieved long time ago and hasn't been beaten. The Rayleigh limit hasn't been beaten directly. And this is not enough for most stuff. Today I work in biology lab, so I just gave a biology info. But biology, you want to study atoms, DNA, proteins, bacteria, viruses, organelles, and for conventional light microscope, you can barely see most of them. So this is not enough. We need more resolution. What can we do? Sorry. Of course, we don't need to restrict ourselves to visible light. We can use smaller wavelengths. So you have higher energy radiation. For example, electron microscopy, you can get much, much higher resolution. I show examples. This should be playing. I show examples from my lab. We do electron microscopy. You can have different scales. So here you have a cell, organelle, and a small virus. This is all very useful, but it also has its drawbacks. So we cannot do live imaging with at least biology and electron microscopy. You have to freeze everything or chemically fixate. So you just have frozen things. And you want to see cells or molecules living and moving apart and see how they interact. You also usually have a smaller field of view. You cannot image lots and lots of cells. Just you have to take a lamella or a small piece. There's also like electron microscope. There's very strong radiation damage, so it is like the electron beam is like a ray of death going to the cell, and it just explodes everything. So you have to use low power, but even so, you have to do a lot of things to protect the cell, low radiation, everything, and there are lots of cases where this is not applicable. So we still need light microscopy. It's still extremely useful. There's a lot. I mean, it's still ubiquitous in biology. This should be playing. I don't know if it, yeah. And this is also from our lab. We do, it's called lattice light sheet microscope. And you can see this is like a cell, and we tag them with fluorophores, and you can see the endosomes entering the cell and how they interact, how they deliver their cargo and everything. So light microscopy is still very useful, despite the existence of other techniques. So, but we need light microscopy, but the resolution is too bad. So what can you do? We can cheat. So we can go around the resolution, the Rayleigh limit, by breaking the assumptions of its derivation. So they had the initial assumptions. I just summarized them here, and we can break each one of them, or more than one of them, or all of them, and get super resolution. And super resolution means any technique that goes beyond the Rayleigh limit. So for example, if you break the uniform illumination and instead you do some structured light or some gratings or something fancy on the light that images that hits the cells, for example, structured illumination microscopy, you can have resolution improvement. Or if instead of not using coherent light, you do some fancy setup with coherent light, or even quantum sources like squeezed ones, you can have more resolution. Or if you don't restrict yourself to the far field, you can do scanning near field microscopy, but going very, very close to the surface that you want to image and getting the evanescent fields. You can give away linear optics and all this fancy super resolution techniques, TED, Palm Storm. We can even get to like 10 nanometer resolution or something like this. And this one I'll talk about later. But however, in doing so, we lose a lot of generality. So basically, you cannot do for everything. Like for far field, you can only image certain surfaces. For nonlinear optics, you have to exploit certain properties of certain particles that are not ubiquitous. So today, in the field of super resolution microscopy, there's so many techniques. There's basically like every experiment you want to do, there's a different technique for it. It's billions of techniques. It's easy to get lost. And I mean, it's working, but it's also expensive and complicated, and it's getting ever more complicated. But kind of works. But it would be nice to have something that is more general, more applicable, or universal than this. I'll start now. So this is the setup. Why do we need? What do we want to do? We want to, with a general method to increase the resolution of optical microscopy. Now I'll review quantum metrology a little bit, apply it to this problem to show how I can get that. So everything I said about optical microscopy has been known for centuries. And in the past, I don't know, 70 years or something, we had computers, and people had the smart idea, oh, we can cheat the Rayleigh limit. We don't need to obey it, right? We have the typical setup. Instead of the eye, we have the camera, and we we measure, take pictures, put in a computer, and then analyze them. And they say, oh, you can use data processing, process the data, and you can get better resolution. So for example, you can do deconvolution. So as I said, this is like below, I have two sources below the Rayleigh separation. And if you look at them, just look by eye, you cannot separate. That's why Rayleigh made his criterion. But if you have a computer, I mean, you know there are two sources here, and you know this is like, let's say, a Gaussian on area function. You can just invert it, right? You know the function, you can just divide in Fourier space, and you can get, right? It's obvious, right? And indeed, you can use Richard-Lucy or any the convolution techniques or any other statistical techniques improve the resolution, not infinitely, but you can get much better resolution by this. So, are we really fooling nature by just putting things on a computer? Actually, no, because the resolution of data processing is also limited by physics. But now, not by the wave nature only, but by the particle nature, because when you collect like the light, it is not like a perfect like area or Gaussian function. You have a bunch of dots, you have detections because of one, by the short noise, the discrete nature of photons, also because the detection, even if it were continuous, the detections it quantizes the results. So in the end, you have a bunch of data points, and you want to do statistical techniques on these data points. but the amount of data points you have or the quality of them also is limited. It limits your ability to increase the resolution. So, but Rayleigh criterion does not talk about this at all. It's just a simple criterion for like the wave nature of light. So we need new bounds. We need a new definition of the resolution limit. And this, for that, we use metrology or parameter estimation or statistical estimation. I will use quantum metrology here, so I don't have to explain metrology and then quantum metrology. I just explain everything at once. But of course, you don't need quantum metrology to explain this, but I will do it. So the quantum metrology is the framework we're going to use for the rest of this talk. And the idea, or a simplified version of it, is that we have a quantum physical system expressed by, let's say, the density function. And it has a bunch of parameters encoded in that. So some phases or some distances, some like physically measurable quantities. And you want to estimate those quantities. So to estimate that, we have the system, and we have possibly many copies of the system. We can do a measurement, a POVM, if you're familiar with the terminology. We can do measurements, quantum measurements on this system, and for every measurement you get data, and then you collect the data, and we have the data here, and we have to use this data to estimate these parameters. So you have to divide some data processing technique here to use. It's basically a function that takes the data and outputs a value that you want this value to be related to the actual ground truth, which is the actual values that were there. So if you have a fixed physical system, you have a fixed measurement, you could do also some fancy preparation, state preparation techniques here, but I will not focus on that. If you have a fixed system and a fixed measurement, you have to find a good estimator for the parameters. And you can choose any function, right? But what makes an estimator good? So in general, you want to minimize the bias and the variance. It's a classical problem in statistics. Variance is the spread out of the possible values. The bias is how close your estimate is to the actual ground truth value. For simplicity, we work with unbiased estimators. So we're going to derive bounds just for estimators that have no bias. It's just a trick to make things like when people from statistics suppose that everything is Gaussian or normally distributed. It's just something to make our lives easier. But then we just want to minimize the variance or the covariance matrix of the other parameters. So we have a setup. We have the parameters we want to estimate, the physical system, and a measurement. So what's the best precision you can get? What's the smallest achievable variance for any estimator? Because an estimator could be anything, but we need a bound, general bound for this. So for all possible estimators, what's the best variance? And which estimators achieve this variance? Could we define the estimators that achieve that? So this is the cornerstone of metrology, is the Kramer-Rao bound. It says that the covariance matrix of the estimator is lower bounded by the Fisher information. And the Fisher information in this case is a vector of parameters, a general case. Fisher information is a matrix, and is basically here is the upper bound actually by the lower bounded by the inverse of the Fisher information matrix. This is just to nitpick, this is a matrix inequality, so it basically means that this minus this is positive, semi-definite, and this minus just the matrix inverse or pseudo-inverse. So this is like an average of this score function, which is related to the probability distribution that generated the data. People might know the Fisher information by this expanded form, or with the derivatives of the score of the log likelihood. But basically, the covariance of any possible estimator is bounded by the Fisher information. So the Fisher information, it gives us like fundamental bounds of what can be achieved, and it can be used as criteria for resolution of what can be achieved for a given physical system. So now the Fisher information gives what's the best variance you can get, best precision, but how can we get this precision? Which estimator gives that? There is no recipe. Sorry, I skipped something. Yeah, there is no recipe, but there is one measurement that is guaranteed to achieve is the maximum likelihood estimator. So it's not something very practical, but it's something that works in the very large limit. So if you have many identical and independent copies of the physical system, let's say we have the sample and we're collecting many photons from that sample in sequence. We have many independent copies. We can factorize the Kramer-Round bound. We can have this bound here on the number of objects. And if you have a very large number of copies, we can achieve the Kramer-Round bound by the maximum likelihood estimator. And this is not very practical. First, because it only kind of works in infinite number of measurements. And for finite, it's not necessarily good, and also it's not very useful in practice. It's just a theoretical tool. But it's good to derive bounds and prove that things exist and everything. But the main thing is that there is a recipe for at least one estimator. Of course, finding actual estimators is like a more art than science. This is what people do in data processing and today machine learning and everything. But there is one that can achieve the Kramer-Round bound. So we have some sort of definition, like given the state, given the measurement, we can know what can be achieved. But there's more. We have the state and we have measurement, but we can have many measurements, many ways of measuring a quantum system. And the powerhouse of quantum metrology is like this very powerful quantity, this very powerful this very powerful theorem called the quantum version of the Kramer-Round bound, which we have we have a bound on the covariance of any estimator. Also, this is the classical bound, but we also have a bound on any possible measurement. So we just have the quantum system. We just say, hey, I want to measure this system. What's the best possible measurement? It tells us what's the best possible precision we can get for any possible measurement we could even think of. And then once we get this measurement, then we use let's say, the maximum likelihood estimator to get the best possible estimator on this best possible measurement. So it's like a very general bound. And this quantity now is the quantum Fisher information. So it's like the quantum version of the Fisher information. It resembles the previous form. Instead of multiplying the score function, we have now the quantum score function. And we just have the anti-commutator. And this quantum score function is defined implicitly via the Lyapunov equation. This is just details. For completeness, don't need to focus on this. But this is the main quantity we'll be focusing about on this talk, and is what people focus on metrology. There are many limitations to it, but this is very useful and practical for us. So basically, they have the system, we have the best possible bound of any possible measurement is dictated by this quantity here, the quantum Fisher information. So now, as before, how can we achieve it? Which measurement, is there a measurement that can achieve it? Which measurement can achieve it? And if you're estimating one scalar parameter, you have the SLD or the quantum score, you just take these eigenbases, you measure the state in these eigenbases, you have a quantum optimum measurement. Quantum optimum means that achieves the quantum bound. So we have also a recipe for finding the best possible measurement, or one of the best possible measurements. However, this is for one parameter. If you have more than one parameter, each parameter will have a best possible measurement for it. But if you want to measure all of them simultaneously, or estimate all of them simultaneously, these different measurements might not commute with each other, so it doesn't work. So if this happens, it can happen, then we might not have a measurement that can guarantee a best possible precision. So this is just a nitpicky detail, but it's going to be important in the end because for our case, we still haven't found possible measurements. But it's good, it's like an existence proof that you know, oh, you have this quantity that's supposed to be the best possible precision, but there's no guarantee it can ever be achieved. So if it cannot, then it's a bigger problem. But when can be achieved? One simple solution is that, or situation is that if the quantum score functions commute with each other, then the measurement bases commute with each other, then they are compatible, then you can achieve the ultimate quantum bound. However, this is very restrictive. There is a weaker thing, a weaker requirement. All of this is active research. There's a lot of people in Poland rederiving these bounds, and this is old. I mean, the last time I looked at this was 2 years ago. There might be very new results, stronger than this, but basically, the best I know is that the weak commutativity that says that if the SLD operators commute on average, then you can saturate the quantum bound, and vice versa. However, the only if part only holds if we allow collective measurements. For now, we're only talking about, we have a system we measure, it's sequentially many copies of it, and a different measurement on each copy of this system. But if we expand this for collective measurements, or say multifocal measurements, for example, like entangled measurements, where you take many states at once and do a bigger measurement on that. If you allow for this relaxed condition, then this becomes if and only if. So this is like a decision tree for a system. You have your system, you calculate the quantum Kramer bound, or the quantum Fisher information, you see what's the best possible precision you can get. Then you need to know which precision can I get this precision. So you estimate the weak commutators. If they commute, if it's 0, then it's fine, you can achieve this. But if they don't, if they do, you can achieve it. You don't know how to achieve it, but it's fine. If they don't, then there's no optimal measurement. You can get close to it, but you don't really know what's the best possible you can get. But even if they commute, you know there is a measurement out there that works, but it might need collective measurements, which is more complicated. So we still don't know that. So it's like a decision tree. You have to get to the bottom. The best you can get is, oh, it's achievable, but I need a collective measurement. And again, as the maximum likelihood estimator, these bases are not very useful. They are usually unphysical because they're just a mathematical construct. And in practice, you have to, the bounds, you just say, oh, this is the best possible I can get, and then you just work to try to guess or have illumination from God to find the actual measurement that achieves this or gets close to it. So it's like an existence proof, but not constructive. And usually, these bases or any other bases, they might depend on the actual ground truth values. So like the measurement will have a dependence on the values you're trying to estimate. It's like a chicken and egg problem. So for this, you have to use some adaptive estimation methods. So it's like you spend some time finding the parameter, then you use the estimate of this parameter as the measurement, and then you estimate again and stuff like this. So back to microscopy. Maybe this was a bit rushed, but I hope everyone could keep up. We're going to apply the quantum metrology framework to our problem in microscopy. So we define the state as the source of light, the source plane, and its propagation. Of course, we could put whatever we wanted here, theoretically, but especially in microscopy, and especially in astronomy, like all this framework can be applied to astronomy and galaxy or planet detection and everything. Especially in astronomy, you cannot put whatever you want here. You cannot put a probe here or a beam splitter here or whatever. You cannot really control. You can control in microscopy, but it's usually hard and specific. So we want a general method. So we just assume this is given and we cannot influence this. What we can do is choose the measurements. So once we collect the light in the aperture plane, you can do whatever you want with this light, put some interferometer, beam splitter, whatever, put the black wall and collect nothing, whatever you want. And we can also, we have the camera here, we detect photo detector, we can put whatever you want as well. We can have a heterodyne detector or phase detector or whatever you want here. It's the measurement part. And we have the estimator, which is we get our data, however it is, and we go to the laptop and we process it and we go do some estimator. And then we look at the results, and we have an estimation for the source parameters. So this is how we put it in the metrology framework. Now, back to the problem of defining resolution or Rayleigh criterion. we're going to define this problem of two point sources. So for simplicity, consider one dimension problem. We have 2 point sources, x1, x2. They are centered, let's say, at the origin, the modeling, and they have a separation theta. And in the image plane, of course, they're going to get convolved by the point spread function of the microscope. They're going to get like this larger support here. And we want to estimate the separation of them. So this is the parameter we want to estimate. And this is muddied because they are overlapping here. So if they were just thin, it would be very easy to find them. But they are overlapped here, so it's hard to estimate. So for here, again, we are talking about incoherent light. I'll just be specific. We're talking about weak coherent light, which means there's no multiphoton events. This is most of the light. You have like light from the sun, light from the fluorophore, everything. It's much more ubiquitous than strong incoherent light. Strong incoherent light, you only have it if you want to. Let's say I want to generate this light, and then I'm going to have. In general, you have weak incoherent light. So you can approximate the quantum system by you have the vacuum state and the one photon state, and you disregard every other. Epsilon is the strength, like the photon number of the photon count. So we can ignore higher order events. And the vacuum state has no information, so you won't affect the Fisher information. So just take the one photon state. And if you look at how it looks, we have basically two terms. And basically it's like you have the position operator spread out by the point spread function. So basically, if the point spread function is very thin, you just have two delta functions. You have like a diagonal quantum density operator. But because of the finite aperture, because of the diffraction, you have overlap. You have some sort of coherence here, and you cannot tell these states apart. If you could tell them perfectly apart, then the problem would be trivial. You have infinite resolution, but you cannot. That's why I have limited resolution. That's why they have the resolution limit. And then you have this light, and you do photo counting measurements of it with the camera, for example, photo detector, and you get this probability. The very simple term, just two Gaussians, or just two whatever function it is. And you just collect data from this, and you find an estimator. So you can estimate the Fisher information for this classical distribution. This is per photon, so normalized by the number of photons. And what you get is that if the sources are apart, or you can tell them one from another, so the Fisher information is constant, more or less, very large, so you have a good precision. But then, when they start to get close, the Fisher information just goes down. This means that the bound on the covariance, the best possible estimation precision goes down too. Have less information, and it starts to go down around what would be the classical Rayleigh limit. So now we have like a new version, or like a fancier version of the Rayleigh limit that accounts for both diffraction and shot noise. It basically means that we can estimate however we want, have a constant information about the sources as they are well separated. When they start to get closer, the estimation goes down, and this is like a exponential kind of like exponential decay. This is the limit to the resolution. This effect of decaying Fisher information, and Tsang called this the Rayleigh's curse, just to differentiate from the actual Rayleigh criterion. So it basically says, oh, for microscopy, with all these assumptions that I laid down in the beginning, two sources, they start to get closer to each other, the precision goes down, and tends very fast to 0. This is the resolution limit. If we put all the data processing stuff that the guys were thinking about, oh, we are achieving super resolution, we are breaking Rayleigh's limit, they are not. If you put them in this framework, they are all going to obey this framework. So now we have a precise definition of what's resolution, super resolution. You have less, here, this or less than this is just regular Rayleigh limit, diffraction limit system. If you break any of the assumptions and you reach this region here, then you have super resolution, actual, real super resolution. So we have this new criterion. So why did it bother to go all of this just to get a new limit? We didn't do any new physics. Then, also just to recap, we have the limit is based on the number of photons. And the more photons you have, the better precision you have. So why don't we just collect more photons? Are they stupid? So the problem is that we cannot just keep collecting billions and billions of photons for each measurement, because, for example, for biology, if you keep imaging, if you put very strong laser, it's going to kill the molecules or the fluorophores. Also, if you have a very long exposure time just to get more photons, you sacrifice temporal resolution, so the particles are moving, but you just get an average or a blurred average of that. So this is a crucial aspect of microscopy. So we just cannot have a large n. Basically, the idea is to have the smallest possible n number of photons that we can still see the stuff. So this limit is an unbreakable wall. As I said, if you have something here, it's super resolution, but you cannot. Nature doesn't allow you to go here. This is unnegotiable. So it seems there's no way around. So okay, so are you doomed? So what can we do about this? But this is all Fisher information. Haven't found the quantum Fisher information. So we are assuming that we're going to do the measurement is doing direct intensity detection of the photons, but we can do other stuff. We're not tied to this. This is where Tsang's discovery comes. Tsang did basically something very basic, something very simple. He just took this problem, estimated the quantum Kramer-Round bound, and he found that there was more, that we could get more resolution out of this. And he also found the quantum optimal measurement that could achieve this. And this gave rise to this field, the quantum-inspired super resolution. It's inspired, as I said, because we use quantum metrology, but for inspiration, but the systems are completely classical. And when he estimated the quantum Fisher information, he found, let's say, for a circular aperture, this is 1D, so just top hat aperture, it's just constant for any separation. Like if you have 1/10 of atom, 1/10 of the Planck scale between two objects, we can still have a fixed estimation. So at first hand, you say, oh, this is crazy. Like I can get infinite resolution. Like there's no really curse. Like I can just achieve all my dreams. I can have like a telephone lens, and I can do some fancy measurement, and I can have infinite resolution, infinite separation of sources. So this seems suspicious, and seems too good to be true, because it is, but this is what the quantum Fisher information is. It's just constant everywhere. But this, as I said before, we have two sources. They are perfectly centered. What this means, I mean, this is just a theoretical model. In practice, means that we perfectly estimated the centroid of that. But how do we estimate the centroid? Like, we have to measure, right? So there is an uncertainty in measuring the centroid. So you have to have parameters at the same time. And if you do this, which is the realistic situation, then you don't have this free lunch that you had here. In practice, if you have to estimate both, this zeta is the kind of the relative displacement of the centroid, you don't get the quantum bound anymore. You have a very good bound, but then it falls down to 0, because you cannot have infinite resolution. It's insanity, right? So if in a realistic scenario, you have to estimate the centroid, and you don't have infinite resolution anymore. So, okay, you're going to say, okay, so what's the point? So this is bad, this is nothing. But yeah, this is bad because it's not free lunch, but still better than direct measurement. This is the Fisher information for direct measurement. This is for a Gaussian point-spread function, so this is simpler. It falls down, as all of them fall down to 0, but it falls down faster than the others. So the quantum, even in realistic scenario, the quantum Kramer-Round bound says that, oh, there's some measurement out there, we don't know which one, that you can get better, so you can get super resolution somehow without breaking any of the hypotheses. So you have a general super resolution, universal super resolution, better than direct imaging. So, okay, we know this is the state of what we have, so how can we achieve this? But first, let's think about where this advantage might come from. because it kind of does make sense. Where is this stuff coming? So we have our hypothesis, and we used, I didn't show the derivation because of limited time, but we use all of them except this one, intensity detection. Because this is part of the measurement. I didn't specify the measurement, I just specified the quantum system, and I used the quantum Cramer bound, which is over all measurements. So I didn't specify this, and this is actually what we were missing, these 200 years, 150 years of related criterion. We were only thinking about intensity detection. We were not thinking about more general stuff. Actually, people were thinking, but they just not using the fancy quantum metrology, so they didn't have a fancy justification for it. But so then why are we losing information with intensity detection? We know that intensity detection discards the phase information of light. So if you have coherent light, we are losing the phase information. But this is incoherent, so spatially incoherent. So what are we losing in this case? And so the explanation for this advantage, or for this result, is the simple result. It follows from Fourier optics. It's the Van Sittert-Zernike theorem. I can demonstrate it by this video. I didn't know it had sound, sorry. But it's just a bunch of ducks going in the water. You have a bunch of incoherent sources of waves. They're all incoherent, but in the long run, they kind of become coherent. You know, in the source plane, they're incoherent. In the far field, they become coherent. And this is how this whole stuff works. It's just a bunch of ducks. Sorry. And the idea is that you have incoherent light, but as it propagates, as it goes to far field, it picks up some coherence. So it becomes partially coherent. So for example, if you are close to the sources, we have an apple and an orange here. Here, the light is incoherent, and nearby is mostly apple. Here is mostly orange, so it's still incoherent. But as you go further, as you propagate, these paths, they become kind of indistinguishable. And so that's why this indistinguishability ends up to the piling up of some partial coherence. And as you go to far field, where the microscope is, you pick up some partial coherence, you pick up some spatial correlations in this case. And if you do direct detection, you discard this spatial information, this spatial correlations information. But if you don't do direct detection, you do some fancier measurement, we don't know yet, you can maybe, at least the quantum bound tells you that there is a way, there might be a way, that you can exploit these spatial correlations to improve the resolution. So how can you do this? And this is the second question that Tseng answered. He found an optimal measurement, and he called this SPADE. I might be running out of time, but the main result is that you have the light, you collect the light, you go to the image plane, and you choose some basis of spatial modes. For example, here I choose this Hermite Gaussian basis. It's just a complete basis. You divide the light into all these components. You like do some mode sorting. You detect, then after this coherent processing, you do direct detection on the individual components, and you get the data that you want to use for the result. And this coherent processing is what allows you to mix the spatial correlation information with the intensity information so that it can be picked up by the detectors. This is what allows you to do the super resolution. And is this, as going back to the diagram, we had the data processing here. Now the fancy stuff is the optical processing here. So it's kind of a fancier data processing. Just a disclaimer, I was using the circular aperture. From now on, I'm going to use a Gaussian aperture just because they do all the results on this. The formulas are much simpler. If you apodize these first lobes of the area function, you get the Gaussian. Just so we can get some formulas. So the previous function that I had some stuff here is just is simpler. It's just the Rayleigh curse is just going straight down to 0. The quantum limit is still constant, and the quantum Fisher information value is related to the aperture, and it's more or less this value here. And this measurement that Tsang found, the spatial mode, the multiplexing of SPADE, He chose Hermite Gaussian basis. You can show the first few elements here. And it's matched, the width is matched with the PSF, which means that the point spread function is matches with the zero order term. He also made a simpler measurement called binary spade, where instead of measure every possible component, you just measure the zero order and all the other ones. And then it's not good for large separations, but for a small separation of sources, it's good. It's a limited but much simpler to implement measurement. I'm just showing the results here for the two apertures I've shown. I'm going to go back to this just to show how this whole stuff works. Also, as I said back, for misaligned sources, the quantum limit goes down, and the spade, since the spade is quantum optimal, it just follows the quantum Kramer-Round bound, goes down as well. And for the binary spade is simplified measurement is not quantum optimal, only for small separations, kind of follows this curve. This is what Sang found, and this is what made people interested. And I'm going to talk about what has been progressed on theory and an experiment on this briefly, because I think we are already out of time. But there's been a lot of research on this, trying to understand, because all of this seems esoteric. Sang is not a very good communicator. He has a very weird, very mathematical style of writing. People could not decode him. But one of the first things people found is that trying to understand this spade measurement. So why do you use the Hermite Gaussian basis? So they found out that they belong to a kind of family called PSF adapted basis, where basically you have your point spread function, you get some polynomials based on this point spread function, and like tailored to this point spread function, and take the Fourier transform, you have a mode basis that is optimal for this point spread function. For the Gaussian point spread function, you have the Hermite Gaussian basis. For like a top hat function, you have the Bessel basis. So basically, for every point spread function, there's kind of an optimal basis. Any basis can achieve the bound with billion components, but these optimal bases, they achieve much faster. Here I show Gaussian aperture with the match, which is the blue, and the unmatched, which is the red. And the blue achieves faster. The red actually doesn't achieve, but if I go from 20 to million, then eventually going to achieve. And when I inverse the situation, then I have the inverse thing. So the Hermite Gaussian basis is part of a family. That's the justification for the Hermite Gaussian basis. Until now, we did imaging for just 2-point sources, but we are interested in general imaging. We're just interested in a general object. In quantum estimation, like we had just 1 parameter or 2 parameters to estimate. Now we have infinite parameters, because an image can be anything. So it becomes complicated, and Sang himself has been deriving crazy quantum bounds on this complicated problem. But you can take slightly simpler approaches. Just want to have a rule of thumbs to get an idea or a feel for how this works for general imaging. So the main powerful one from this paper from Sang himself is estimation of geometric moments. So let's say we have a general image. We parameterize it by its geometric moments. We just want to estimate these moments. This is just a way to parameterize an infinite parameter problem to a still infinite, but at least a countable one. The things are better to understand. So we define the geometric moments as the moments of the distribution. We have the width of the image, and Sang was able to find some scaling bounds with respect to the size of the image. So what he found, in summary, is that for first-order moments, so let's say estimating the centroid, quantum Fisher information and Fisher information for direct imaging, so the quantum case and the classical case are the same, which is kind of, we know. For second-order moments, for example, the separation of 2 sources, then we have this infinite resolution thing. But for 2 sources, perfectly aligned sources, this is infinite resolution, but in practice it's not. It's just a second moment. For higher order moments, they still fall to 0, but we still have advantage of direct image. So this whole stuff holds for our general imaging, but the idea is that it's just higher, if you think about it, just higher order moments, geometric moments that are advantageous. So if you use spade for this, For even order moments, spade is more or less close to the quantum limit. We don't have a tight bound, but it's near optimal. But for odd order moments, like 1, 2, 3, 5, 7, it's unable to. It doesn't estimate them at all. And this is because the spade modes, the pad bases, have well-defined parity. Like, for example, the Hermite Gaussian modes, they are odd, even odd, even odd, even odd, even odd. They are this very well-defined parity. They always have well-defined parity. So if you estimate them with the odd moments, have the integral becomes 0 all the time. So they are insensitive to this. And this sounds odd, it's just because they're originally meant for just 2 sources. If you want to apply them to general sources, they're not so good. So one solution is just to have an image. If you use them in practice, you have an image, they make like ghost images of this, whatever you're trying to measure. So if you displace the modes or the reference of the modes so that the image lies in one quadrant, then the ghost images separate, and then since here the odd moments are all 0, then you can estimate the image. A better way is just use a superposition of these modes. So they call the IPAD or interferometric pad basis. Basically, you use 7 bases. So you kind of like 7 different measurements and have to divide by 7 to compare the fish information. You have these 7 measurements with different superposition of modes, example here. And now you have you break the well-defined parity of the modes, and then you can estimate all the moments. This is just fancy ways of making spade work, but it also has many limitations. So for Hermite Gaussian modes, as you grow, they cover larger areas. So if you have just a few modes and the image is this big in the image plane, then you cannot see what's outside. So you need higher order modes, but higher order modes are hard to produce and everything. So this is very limited, just using them directly. So they're localized. Maybe you could use some sort of scanning mechanism to improve them, but these are all limitations of spade. In general, for all these methods, this is the quantum limit, direct imaging. These methods, they're even not optimal for large separations. They become optimal, not optimal, but better. They become super resolution for small separations. In a log plot, you could see this better. But they become resolution for small separations, but they are still not also optimal. Maybe there is a measurement that is optimal. We don't know. It's an open problem. We know that it's achievable because of this weak commutativity thing that I talked earlier. So there is a quantum optimal measurement, but we don't know which measurement. We don't know if maybe they require collective measurements. We don't know. These are open problems, if anyone is interested. But I've talked about lots of limitations of spade, so why are we even using it? And the main reason is inertia. So basically, Tsang found a way to achieve the bound. There are infinite ways of achieving. This is just one of them. And this is extremely problematic. I'm not even talking about experimentally, which is almost impossible. But this method is basically just for 2 sources. It's good for separating the even and odd components of the light. That's why it gets infinite resolution if the sources are perfectly centered. But for general, they're not so good. But people still trying, most of the field is trying to make it work. Maybe that's why it's stagnated, because they're still trying to make spade work because it was the first one that was found. Finding others is hard. It's simple to understand. It's not adaptive, so you don't need to keep changing with the data. And inertia, because just they're trying to prove that it works. There's also the effect of the light source. People extended these results for coherent light, partial coherent, strong incoherent, even quantum sources, squeezed Fock states and everything. For 2 sources, we know that entangled light, like squeezed light, you can go double the quantum Fisher information with respect to incoherent. There are people discussions about coherent light, but it's not so good. But there are only very limited results on quantum light. If you want to work on that, there's a lot of low-hanging fruit for that. And there are also many other results. They extended this idea to temporal estimation or even non-imaging estimation, and doing 3D imaging now using axial separation of objects, applying this to astronomy, other techniques, and also different fancy ways of doing the statistics. For experiment, I tried to rush. But there had been many experimental demonstrations just for true sources, which is the simplest possible example, not practical in real life, but easier to implement. These are the first ones, but none of them is actual a microscopy experiment. It's not like we have two sources separated by a few nanometers. A few nanometers, and we need a fancy objective, and we tell them apart. It's just like two sources separated by 1 centimeters or a few micrometers, and we use a bad lens, and we show improvement of this bad lens, so it's just proof of principle. Not a real microscopic improvement. For general imaging, there's also only proof of principle, not a real microscopic improvement. I haven't kept up with the literature, so I just show what my group has done. And also, we don't do the fancy photo counting to get the actual Kramer-Bound Fisher information. We just show a vibe check of this. Mode sorting is very hard to implement. You need very exquisite control of spatial light modulators to get, or like some crazy proposals like this one that you bounce back and forth from spatial light modulator to have a sequential transformation. We could also try fixed phase elements and everything, but it's still very hard to implement. An alternative which we use in a model is, instead of doing direct mode sorting, we do heterodyne detection. And the local oscillator is just the modes that we want to measure. So it's like, instead of simultaneous estimation, do a sequential estimator. Estimation is very inefficient, but kind of works. Then you also have the problem of finding good estimators, because the data processing, because we have the photocurrents that we have from SPADE, how to turn it into the object, because it's not a direct, you don't have an image now, you just have a bunch of numbers that is hard to interpret. For example, for heterodyne, you just have this. This is what you get from the microscope. So what the hell is this? We want the image, so what the hell is this? So we need some formulas to get from this to this, or to this, but since the model is very good as a double-edged sword, as the first talk they talked about, the model is very sensitive to the environment, it's good, but also bad, because it's also sensitive to parameters, but also sensitive to the environment. So it's very hard to get a good estimator. People have been trying numerical analytical solutions, but what works best is just using deep learning, because it solves everything. And the future directions, we have to make a microscopic implementation of this in experiment. And also in experiment, we have not only implementation that works, but implementation that is practical and useful, because you can make implementation with post-selected photons that happen every other day, but this is not practical, because your cells are going to die before another event happens, right? So something that is practical and useful for actual microscopists, either in biology or material science and everything. And this is not only experimental, the goal of the field is experimental, but we need theory, because the theory you have, I believe, is not good enough to achieve this. If we just keep the theory as we have and try to brute force our way through experiment, it's not going to happen. And there are a lot of many questions, mostly here in theory, like general imaging, as I said before through the talk. And my vision, which is a crazy vision, that SPADE is the dead end. The best measurements will have to be adaptive, or they have to be learned, like with deep learning, like I showed before. And it's going to be overly reliant on processing. And I think eventually the ultimate microscope is going to be something like this. So you just do, instead of you get the light, process the light, and do the data processing, you do the processing before detecting the light. So it's kind of like a smart microscope. You can even say optical neural network. My supervisor who work on that also works in parallel with this, so the ideas cross. But it's like some sort of intelligent or smart microscope that learns how to do the processing even before we detect the light. So they can best utilize the spatial correlations, and then once we get to the actual measurement, we get like the post-processed version. It's like a post-processing before detection. And if you want to learn more about this, there's this review by Tsang. It's talking about starlight because he talks more about astronomy, but it's the same for microscopy. I just talk about microscopy because what I know very little of starlights. And a bit of self-promotion, but I have my PhD thesis. This is a good tutorial to start with this. It's very didactic for you to understand. Sorry for rushing. Hope you liked my presentation.
Thank you, Inácio. So given the time, I think it would be better if we break now for lunch. Might be a bit tight, but let's try to get here around 1:30, so we don't postpone too much the end. So we'll be back here for the round table, and then the questions you have for Inácio we can ask later then. Okay, so let's thank all the speakers and Inácio again.